Welcome everyone. This video is intended to demonstrate the particular style and deceptive tactics being employed, intentional or not, and the erroneous reasoning that leads to it. Here's a look at F.E. Dogma's analysis of LIGO, Hanford. A link to his video is in the description.
This is a photo of the Hanford LIGO Observatory in Washington State. It is an interferometer, and each arm has a beam tube that is almost 2.5 miles in length. Now the light that enters these beam tube actually reflects between two mirrors at each end about 300 times.
Now it is the alignment of those mirrors that is most critical, and what they did is they actually hung them from a 4-segmented pendulum to help isolate them from outside vibrations.
We can say at these high frequencies we're limited by noise in this observable, so we're going to reduce that noise, and we're going to increase the noise in the other observable that we don't care about at those high frequencies.
I've made a pendulum out of just parts we found around here just to demonstrate why we use pendulums for seismic isolation. By seismic isolation, we mean that whatever's hanging at the bottom of the pendulum moves less than the ground. So you imagine my hand as being the ground, and if at very low frequencies of my hand motion or ground motion, whatever's hanging down follows the ground exactly. So there's no isolation there. And then as the frequency gets higher, you see that you get this place where the pendulum, the thing hanging from the pendulum, moves more than the thing you're trying to isolate it from. So that's actually the wrong way of seismic isolation, right? That's making it worse. But as you get to even higher frequencies, then you start to see that it actually really does isolate. My hand is moving way more than the thing hanging from the pendulum. Notice how the pendulum at this level is moving a lot less than my hand, and the one down at the bottom is moving even less than the one above it. That's how we keep things still enough so we can see the tiny motions that gravitational waves will cause.
Here's that mirror. You hang that mirror from pendulum, and that mirror is hung from another one and another one. These are just more masses, and so multiple suspensions are used. And so that's one way it's done. Another tricky thing, which you guys might be interested in, especially people in microscopes and biology. Wow. And that is that you actually make a platform that measures the noise and then kills it by forcing the noise to go to zero by driving the table it's on. It's very much like those earphones that kill the noise when you're flying in an airplane. And advanced LIGO has some very fancy things in it. It hangs, for example, the earth is attached to these springs up here, and one way to here's that mirror, which is the suspended mirror, and each one of these is a pendulum. That's another pendulum, another pendulum, another pendulum. You can go home and build this for yourself. Just take a cup, hang it by a thread, and hold it in your hand up here. And you'll notice the following thing. At low frequencies, and a pendulum, the top, which is the ground, moves along with, they move together. The mirror and move together with the motion of the ground. But if you move this very quickly, this thing doesn't move at all.
Alright, so Rainer Rees in his lecture, he explained this concept and told everyone, why don't you try this out? So that's exactly what we wanted to do. So we decided to do an experiment and test out if this quadrupole pendulum actually works.
Yeah, so how did we make the pendulum? First, I attached 4 washers together, and I attached a motor controller to it, to each of the washers, so called a microbit, so it can detect the acceleration of each of the washers using a programming language called Python, so it can see what's the difference in between the speed of all the washers. And the best part about the microbits is that it's wireless, so I don't need to connect the transmitters to the receivers.
Pendulum 1, it still has a lot of vibrations. Pendulum 2, it gets less, and eventually at pendulum 4, again, there's barely any vibrations. Our conclusion is that the more number of pendulum systems you're gonna put, let's say you put a 5th one, a 6th one, the more efficiently it'll work, as in it'll be able to decrease more vibrations.
And one of the
Geometric.
arguments is that this system would only work
Geometrically.
because the pendulum would be like a plumb bob, and this would be the only way that the face of both of those mirrors would be perfectly parallel to each other. Of course, a calculation for the Globers shows that those pendulums would only be out of parallel by 36 1/1000ths of a degree. I think we have the technology to accurately calibrate those mirrors to the correct angle. Also, they actually have to actively monitor those mirrors during use, and they do this with 5 sensor actuators, and that keeps the mirrors within an angular orientation of 10 to the -8 radians.
That if the ground moves, they stay still.
In initial LIGO, our mirrors were suspended as a simple pendulum, which was basically with steel wire looped around the barrel of the mirror. That worked fine for the sensitivity level that we were trying to achieve, but we wanted to take a factor of 10 improvement in the sensitivity, and to do that we had to move away from using a simple steel wire. We suspend our mirrors in advanced LIGO using fused silica fibers, a very pure form of glass.
There's a little thread coming down here. Can you see that? Right on the tip of my hand. It's hard because it's glass and it's so tiny. It's a little bit less thick than a human hair, but these things have crazy tensile strength. So these are the suspensions of our LIGO mirrors.
You wouldn't think you could take a 10 or 20 or 30 kilogram mirror and hang it on just a tiny thin piece of glass. But glass is very strong in that direction. Don't touch it. If you touch it, it'll break right away. The Glasgow group discovered a way of hanging these things on glass fibers and bonding them in such a way that it all became one piece of glass. There wasn't a separate wire that would rub. It was all just like one piece of glass, mirror and the fibers.
Called silicate bonding, which is deceptively simple, but a powerful technique, it turns out, to be able to join our glass fibers to the mirrors. My research on that was concentrated on the kind of bottom end of the suspension, that final stage holding the fused silica mirror. But that itself has to hang from several stages of isolation, because one stage isn't enough to isolate from all the noise to hold that mirror steady.
So the advanced LIGO suspension is in fact a quadruple pendulum, so that's 4 stages to get the necessary isolation from seismic noise or seismic vibrations.
When you have multiple pendulums, one suspension mounted onto the next one, we're really stopping all of the outside horizontal and vertical motions that come about due to movement of the earth. We're stopping all that from hitting our optic.
The beam tubes are the other key component. They are 1.2 meters or almost 4 feet in diameter, and they need to be straight enough so they don't interfere with the laser light.
Horizontal is perpendicular to the vertical. You don't get to pick your own definition. That is the definition of horizontal we are using. Perpendicular to the vertical.
Now here's a very good article explaining exactly how they did the alignment using GPS surveying, and I'll leave a link to this in the description. On page 2 is table 1, which are the allowable tolerances for the beam tube, and this includes the manufacturing process. But if you look here, this is the tolerance from a perfectly straight line that was allowed when they did the final assembly and alignment with GPS, and that was 1.8 centimeters or less than 3/4 of an inch. Now actually at Hanford down here on page 9, they got it to within 1/2 of a centimeter which is less than 3/16 of an inch, from a perfectly straight line, from a perfectly straight line, from a perfectly straight line, from a perfectly straight line.
Where's the horizontal?
Tube is the horizontal.
Now here's a cross-section of the beam tube enclosure, and the closure is a shell made out of concrete. It sits on a concrete slab, and you can see that the beam tube is off-centered. Now after the concrete slab was poured, they used this GPS unit on a cart to mark the center line for the location of the beam tube.
Tube is the horizontal. Tube is the horizontal.
Now the beam tubes were manufactured in 20-meter lengths, and they would move the GPS unit 20 meters at a time to get an accurate centerline position for the beam tubes.
You're also misquoting the surveyors that you're talking to. When they say level is horizontal, they're talking about when they prepare their equipment, they level their equipment and they have it pointing on a horizontal plane. From that, they have their reference point, and it's the deviation on that plane that they're measuring.
Of course, the critical alignment was during the assembly of the beam tubes, and in the photo right here, you can see one of the brackets that is at one of the beam joints. So what they did is they actually put a GPS unit on top of the beam tube, and then they use these adjustment nuts right here. There's two more on the other side until the beam tube was in the proper position.
Tube is the horizontal.
And the other key component is the concrete slab. Now there are blueprints for these projects that are available to the public, and they show the elevations for the top of this concrete slab. So this is going to allow us to understand whether this project was built
geometrically
or on a globe.
I'll leave a link to this website in the description, and I'm going to go to the Hanford Observatory and click on the civil prints. This will give you an index of blueprints. We're going to start with this one, the drawing matrix. Down in the lower right corner is the number of the drawing you're looking at, and this drawing shows the whole facility. And we're going to take a look at the northwest arm. Now the drawing numbers I have circled in red over here match these drawing numbers in the index. Here's the Hanford LIGO Observatory on Google Earth, showing both the northwest arm and the southwest arm. And I've aligned the matrix drawing so it matches Google Earth. Now I've turned everything so the northwest arm goes horizontally across the top, and here is that matrix drawing. I have the corner station, mid station, and end stations lined up. And what I want to do is start by looking at this blueprint here, which is this segment of the arm. Now down here where it says location confirms that we're looking at the correct drawing, and this lower drawing is the overhead of the beam tube, but I want to take a look at this profile of the concrete slab up above. These dotted lines up here show the side profile of the concrete slab. Along the bottom we have distances that are marked off in 100-foot segments, so this drawing goes from 0 feet to 1,400 feet. Over on the left we have elevations that are 10 feet apart, so each one of these smaller lines represents 1 foot. And at every 100 feet we have an elevation for the top of concrete slab.
So I'm going to start with this elevation at 0 feet that is at the vertex of both arms.
Tube is the horizontal.
This is a blow up, and we have an
GPS.
elevation of 533.78 feet. And I'm adding that elevation to the corner station on Google Earth. And next I want to find the elevation for these 4 distances. Those elevations are on these drawings. Here are the elevations. Now we can see that the elevation decreases by 4.15 feet from the corner station out to the end station. So let's compare this to the
geometric
and the globe models. Now on both models, the horizontal line is perpendicular to a vertical line at the location of a surveying instrument, and on both models, a level line is a line of equal elevation above mean sea level. Now I've added water levels to help explain this, but
geometrically,
the horizontal line and a level line would be one and the same, and of course on a globe, a level line would curve down from the horizontal line. Let's start with
geometrically.
Now it would make the most sense if we had the same elevation for the length of the arm. Because one of the
geometric
arguments is that the mirrors on the pendulums need to be parallel to each other and perpendicular to the beam tube.
Perpendiculars to a plane or parallel, yes.
Of course, this is not even close to the actual
GPS.
elevations. It starts at about 3 inches right here, and at the end station it is actually over 4 feet higher. Of course, it would be possible to build this on a slope. And these would be the required elevations using the same rise over run ratio. But that does not match the
GPS.
actual elevations. In the center here, we're just a little bit over a foot lower, and on each side, we're just a little bit over 9 inches lower. And ironically,
GPS.
those elevations represent a line curving up, which of course brings us to the globe. And on a globe, a level line of equal elevation will curve down from the horizontal line. So this is a globe level line of 529.63 feet. And this is a horizontal line that is tangent to the end station. Now what I drew down here is just a smaller representation of this graphic up here showing curvature drop calculations. So here I've added the
GPS.
actual elevations of that concrete slab, and what I'm going to do is I'm going to do earth curvature calculations for each one of these distances. I'll add that value to the 529.63 foot elevation and see if it matches the
GPS.
actual elevations. So let's start with this
GPS.
elevation here. It is 3,200 feet from the end station, which is 0.606 miles. I'm using the Metabomb curvature calculator, and that gives us a geometric drop of 0.24 feet.
on a model.
I add that to 529.63 feet, and that gives me a total of 529.87 feet.
On a model.
That is off by only 0.01 feet, which is less than 1/8 of an inch.
On a model.
At the mid station, we have a geometric drop of 1.01 feet.
On a model.
That gives us a total of 530.64 feet.
On a model.
And that is off by 0.02 feet, which is less than 1/4 inch.
On a model.
At this distance, the geometric drop is 2.3 feet.
On a model.
Giving a total elevation of 531.93 feet.
On a model.
And again, this is off by less than 1/4 inch.
On a model.
And finally, at the corner station, we have a geometric drop of 4.1 feet.
On a model.
Giving a total elevation of 533.73 feet.
On a model.
Now this is the largest difference at 0.05 feet, but that is less than 5/8 of an inch.
On a model.
Now as I said, I used to work in commercial construction. I was responsible for a lot of concrete pours, and 1/4 inch over 10 feet is an acceptable tolerance. These numbers are very impressive over this distance. 5/8 of an inch is not even going to be an issue, because look at all the clearance she had between the bottom of that beam tube and the concrete slab.
Tube is the horizontal.
And what is very obvious is that these
GPS.
elevations do not work
Geometrically.
It would not even work
Geometrically.
if that slab was designed as a slope, because it would be just over 1 foot low in the center.
On a model.
So my calculations support what was said on page 3 of the alignment document.
On a model.
GPS is based on the center of the Earth.
The fundamental coordinate system for the alignment was the Earth ellipsoidal model WGS-84. So I think it's safe to say that the top of slab
GPS.
elevations for those beam tube arms is more evidence of a globe.
On a model.